Good morning or good afternoon, everyone, depending on where you are in the world. Thank you for joining us today and welcome to today's webinar. This is the fifth webinar of the 5G MOBIX's webinar series on results and lessons learned of 5G for COM from the project's different trial sites. So far, we have looked into the trial sites on Finland, France, Germany, and the Netherlands. And today we have the opportunity to get an insight into the Korean trial site. My name is Seve Christoforu. I am a Communication and Dissemination Officer with ICCS, the Institute of Communication and Computer Systems in Athens, Greece, and I'm also the Dissemination Task Leader for 5G MOBIX. I will be moderating the webinar today, so before we get started, I would like to inform you that throughout the presentations, you will have the opportunity to submit your questions to the question box that you can find on your control panel. We will collect them as we go and address them all at one time towards the end, where we're going to have a Q&A session. In case you're experiencing any technical issues with the audio or not seeing the presentations properly, for example, feel free to use the chat box that you can find again on your control panel to notify the organizers. And now for introducing today's program, I would like to ask the presenters to turn on their webcams. All right, thank you, and a warm welcome to both. So our first speaker for today is Dr. You-Jun CHOI. Dr. Choi is currently a principal researcher at the Korean Automotive Technology Institute, where he first joined as a senior researcher back in 2011. He has a bachelor's degree in electrical engineering, a master's degree in mechatronics engineering, and in 2018, he received his PhD in transport system engineering from the Korean Advanced Institute of Science and Technology. His current research interests are, among others, the developments on electric mobility, CITS, connected and autonomous driving system, and driver status monitoring system. Since 2017, he has participated in various Horizon 2020 research programs as a Korean coordinator, most of them with a focus on 5G-enabled, cooperative, connected, and automated mobility. Recently, he was invited to several more EU research programs concerning, again, the CCOM topic. It is also worth mentioning that in 2019, he was honored with a certificate from the Korean Minister of Science and ICT. Today, he will introduce us to the 5G MOBIX project and specifically the Korean trial side of the project. And then his presentation will focus on the specific use case of remote control vehicle via millimeter wave communication. Thank you so much, Dr. Choi, for being here with us today. Our next speaker will be Dr. Heesang Chung. Dr. Chung received his bachelor's degree in physics from the Korean Advanced Institute of Science and Technology, and his master's and PhD degrees in physics from Cheongdam National University in 1995 and 1999, respectively. Since then, he has been working with the Electronics and Telecommunication Research Institute, ETRI, where he's currently the principal researcher. His career in ETRI began with optical communications and then moved on to mobile and wireless communication systems in 2005. He was involved in research projects related to LTE and LTE Advanced from 2006 to 2010. His current research interests are in 5G, 5G Advanced, and 6G mobile communications, and today his presentation will focus on the use case of tethering via millimeter wave communication. Thank you both for being here today, and we're all looking forward to seeing your presentations. Without taking any more of your time, You-Jun, the floor is all yours. So I will make you the presenter right away.
Thank you. Okay, thank you very much for your warm introduction about me. And then I will present about the brief introduction about the Korean trial site overview. So the 5G MOBIX objective of the 5G MOBIX is developing and test automated vehicle functionalities along with the cross-border corridors and urban trials under the all conditions of the vehicular traffic and network coverages, considering the legal, business, and social and local aspect, as you know where. So actually there are two cross-border corridors consist of the Spain and Portugal and Greece and Turkey. And there are also 6 local trials: China, Finland, Netherlands, Korea, and Germany, and we are from the Korea. And there are the 4 partners: the KATECH, ETRI, and SNET ICT, and 1 associated partners, the RUNO. So the as the trial site reader, the KATECH, we are providing the test site and trial executions, and we are doing the remote driving use cases. And actually, one of the non-profit research institute in Korea, they are providing the 5G NR and 5G NR OBUs, and then they will in charge of the second use cases, the tethering via the mmWave communications. And SNET ICT, which is one of the private company in Korea, they were providing the 5G core networks. And RUNO, they provide the test vehicles. So in the 5G MOBIX, there are several use cases depending on the several frequencies. And most sites initially deploy the 5G NR over the 5G core, which is the 3GPP and SA option 3. We are deploying the 3GPP SA option 2 as a 5G communications. So we got the permission to use the flexible access command spectrum band, which is the 22 gigahertz from the Korean government. So the Korea use cases, there are consist of the 2 parts. One is the tethering via vehicles, and second one is the remote control vehicles, and those 2 are based on the 3GPP technical report 22.886. So, this is the brief concept about our 2 use cases, and you can see the key KPIs in the table up top of this slides, and then more details we will explain later each presentation from the ETRI and KATECH. So we also have 2 trial sites. One is the Yeoju Highway, which is the totally 7.7 kilometers test track, and the section of the 22.7 kilometer is actually used for the trials, where the 5 data units are deployed along with the test tracks. And for the remote control vehicle use cases, the KATECH providing the private proving ground, which is located in the Cheonan area. And this is the 1 kilometer patch of the different type of the test road. For example, the Belgium paved road, straight lanes, and brake tracks. And the only 1 data unit is deployed for supporting the remote control vehicle use case. So we think that there are possible services based on our 2 use cases regarding the tethering via mmWave. we can providing the high quality of the video streaming and holograms and AR, VR things that is in to the passengers who are in the automated vehicles. And regarding the remote control vehicles, we can providing the ODD extensions, especially the sudden weather changes or the automated vehicle faces the uncertain changes on their way to the course. So this is the brief introduction about the Korean trial site. And next, the Dr. Heesang Chung from the ETRI, he will more introduce about the first use case, which is the tethering via millimeter wave communications.
Thank you, You-Jun.
Then can I?
Heesang, we turn to you. Super. We can see your presentation.
Hello, everyone. Can you see my screen?
Yes, we can see your screen.
Thank you. Thank you for your kind introduction, Sabi. And thank you for Dr. Choi for your coordination. Hello, everyone. My name is Heesang Chung from ETRI. So I'm going to present the first use cases of the Korean trial site, tethering by a vehicle scenario. Okay, here we have several topics. I'm going to deal with the first, the introduction to millimeter wave 5G network. Moving on. Okay, as you can see, here we have some overall features of our 5G network system for the Korean trials. Our system is based on 3GPP release 15 specification. And for the radio part, we are using frequency range of around 22 gigahertz. And our 5 network system have a 5G core network part that have AMF, SMF, and UPF. And we also have 5 access network. For the gNodeB part, our gNodeB has the capability of carrier aggregation of up to 6 component carriers. And each component carrier can support 100 megahertz. So our gNodeB can support up to 300 megahertz. For the downlink data rate throughput, it supports about 400 megabps for each carrier. So totally, it can support 2.4 gigabps data rate in the gNodeB. And our gNodeB can support scheduling of 6 connected users at the same time. So this system has the capability of maximum 6 UEs at the same time. For the UE part, our UE has the capability of carrier aggregation up to 3 CCs. So each UE has the maximum data throughput 1.2 gigabps. Okay. So you are looking at a 5G core network to the right-hand side. So you are looking at the picture of our system. There is a 5G core network between the gNodeB and data network. So usually the 5G core network has user plane functions and control plane functions. So so AMF and SMF is dealing with the control plane. They have the functionalities like registration, connection, and mobility and authentication. And SMF is dealing with creating, updating, and removing video sessions. And UPF is dealing with data net interconnection, packet routing, forwarding, per flow QoS handling, and some more functions. For the hardware platform, you can see the pictures of our hardware platforms. We have switches, which is the model number is GNYXB series switch. And we also have a HP server, which is for implementing the ETRI software package for AMF, SMF, and UPF. Also, okay. Here we have 5G access network protocol stacks. Maybe I think most of you are familiar with this type of protocol stacks. To the left-hand side, there is a user plane protocol stacks, and to the right-hand side, there are control plane protocol stacks. There are some common protocol stacks like physical layer, MAC, RLC, and PDCP. For the user plane protocol stacks, we have SDAP, which is dedicated to the user plane. And to the control plane, we have RRC, radio resource control, and NAS protocol stack, which means non-access stratum between you and core network. So our access network is implementing all of these protocol stacks for the service. Okay. Here we have some functions for the RRC, which is also layer 3 of the 3GPP radio link layer. So there are many functions like, for example, broadcasting of system information and RRC connection, and their maintenance and establishment and release. Also, they have the functionalities of maintenance of SRBs and DRBs, which means signal radio bearers and data radio bearers. And also, layer 3 controls the handover and QoS management and many more functions. For the layer 1 and 2, so we have many protocol stacks for like SDAP, PDCP, RLC, MAC, and physical layer. So I'm not gonna describe the full details of each protocol stacks. So let's skip this one. Okay, this is our GNODB hardware platforms. As you can see, there are pictures for overall 2 parts. The left-hand side shows the modem and radio RF module. And there is also a server for implementing L2 and L3 layer. In the table, you can check some characteristics like dimensions, weight, and power supply of each hardware platforms. But for the modem and RF, this is not a commercially available product. So we design and implement it by ourselves. And this is just a prototype. So there is no model name for the commercially available product. And for the L2 and L3 server, it is a supermicron server, which is their model name are like this. There are 2 types. One is tower type, and another is rack-mounted types. Overall, they have the same functions except the type. Okay. Here we have hardware platforms for UE, and as previously mentioned, we have also the modem RF part, which is made by ourselves. So this is not a commercially available product. It's as a prototype. And layer 2 and layer 3 server, it also has a commercially available server. And since it has a lower specification than the GNODB, it's look like a little bit smaller, and weight is a little bit smaller. Then, and actually this server support up to 8 core per CPU. Okay, you are looking at the overall system component of our network. Left-hand side, you can see the 5G core and GNODB layer 2 and 3, GNODB layer 1, and also UE part. We have L1 part and L2 and L3 part. Usually, so we are connecting our smartphones through Wi-Fi access point. This Wi-Fi access point is connected to the layer 2 and layer 3 server by some Ethernet port. And this smartphone can have some services like 5G services like video streaming or some other types of services. In this picture, you can check out that there are several smartphones that connected to our 5G network, and they are showing the video streamings from the video server, which is connected to the 5G core network. Okay, this was that was the brief introduction to our mmWave 5G network. And now, so I'm going to explain some technical characteristics of our mmWave 5G network. Overall, I'm going to explain 3 types of technology. The first part is the beamforming. As you might imagine, the beamforming is one of the key technologies for mmWave 5G, because mmWave usually experience severe path loss than the lower frequencies. So as you can see, here we are using some kind of antenna technologies. There are many antenna elements. If you're using many antenna elements, we can focus the energy of the RF. So we can have a beam width and antenna gain relation like this. So there are 3 examples. If we focus more energy, we can get a larger distance and we can get higher antenna gain, but instead the beam width can be narrower. So there is some relation between antenna gain and beam width. So there's some trade-off relation. So we have to choose what kind of distance, how long distance we're gonna cover, and how large beam width we have to choose. So this is an example of beamforming design and implementation. As you can see in this table, we have some parameters like output power and antenna gain for TX part and RX part. So in this case, we apply the same design for GNODB and UE. So with application of this kind of design, we can have 20 dB signal to noise ratios at the distance of 500 meters. And we also can have 13 dB of signal to noise ratios at the distance of 1 kilometer. So this is just an example. So with this kind of design and implementation, we can get about 500 meter coverage for the 20 dB SNRs. Okay, this is example of measurement. The left-hand side shows the map of a city which I live in. As you can see, there is a number 1 and 2 and 3, which indicate the location of the G-node B. So in the right-hand side graph, there is indication DRU 1, 2, and 3, which means the G-node B 1 and 2 and 3. So with this setting, with this deployment, we measured signal-to-noise ratios while we drive a test car along this road. As you can see, there is measured signal-to-noise ratios and measured data rates. And we indicate the red lines, which means which shows 20 dB SNRs and also 2 gigabps data rate. The measured blue lines shows that for most of the load, we can achieve more than 20 dB SNRs and more than 2 gigabps data rate. Okay. Now let's talk about the beam switching characteristics. To the left-hand side, we have three kind of graph that showing the G-node B and UE. So in the previous calculation, link budget calculation, we assume that the G-node B and UE were facing each other so that we can get the maximum designed coverage. But normally, the vehicles or UE can change direction to the right-hand side or to the left-hand side. For example, if the car is overtaking, you need to change the direction. So frequently, there are some situations in the road, like 1 and 3 different directions. For the different directions, we cannot achieve the fully designed SNRs. So one method to overcome this situation is to combine three kinds of different directional beams, like the picture in the right-hand side. Then we can effectively have a larger coverage of the angle. So this is the one kind of a beam switching technology. So in our system, as you can see here, there is a UE device which has 3 beams, beam 1, beam 2, and beam 3, which are facing different directions so that cover the wider range. And with this equipment, we tested the beam switching characteristics. So this test vehicle has our user equipment on the roof, and we run the test way while we are measuring the each beam's characteristics. The measured beam characteristics show that we have 3 different SNR curves for each beam. For the most part, the red beam, which is in the center, has the highest value. But when we change the directions at the junction for DRU1 or DRU2, as you can see, the maximum SNR's beam is changed to the beam 3 at the case of DRU1 and to the beam 1 at the case of DRU2, so that we can always maintain the largest signal-to-noise ratios with this UE. Okay, this is a brief lab test showing the beam switching functionality. So this is the first version of our UE. So we start the reception functionality. As you can see, the data rate is about 2.7 gigabps, and we can change the modulation and coding scheme we can increase up to about 3 gigabps. This number is possible at the lab. So now we are changing the directions. As you can see, the beam is indicating the different directions, and now it's changing the direction. So the selected beam is changing to the center and to the right. Okay. This was a brief introduction of our functionality and switching functionality. Okay, let's move on to the another topic. This is a kind of handover algorithm. As you can see here, there are 3 different locations for a test vehicle. In case 1 and 3, the vehicle is serving from home cell and target cell. So somewhere between 1 and 3, for example, in the position of 2, you have to switch the serving cell, which is called handover, and you can also check the power profiles of each locations. Okay, this is handover procedure. This is a very complicated procedure. So you can check 8 different procedures for the handover. This is typically for 5G. And there is some typical time duration for each process. So there are 2 issues. One issue is to how to increase the handover success rate, and another is how to reduce the handover interruption time. These 2 are the main issues in the handover, and we focused on the issue of the first issue, that increase the handover success rate. So in our situation, the most important characteristics is beamformed GNODB. You are using beamformed GNODB. So I'm gonna explain this kind of situation by using this graph. As you can see, the serving cell receive power is increasing as the vehicle approaches the GNODB, but as it passes the GNODB, the power decreases very rapidly. This kind of power profile is due to the beamforming of the GNODB and UE. So this is a very peculiar situation for our millimeter wave 5G system. So we have to deal with this kind of characteristics. Looking closer, you can check these red circles. So you can see that the target cell power is increasing very slowly, and serving cell power is decreasing very rapidly. This doesn't happen in a normal LTE or sub-6 GHz 5G radio. Normally, in the LTE or 5G, sub-6 5G situations, the target cell and serving cell has the very similar slope. So in our system, it's very important to trigger the handover in the right time. That is the key. So there are several strategies, but we are focusing on the first strategy, separation of handover preparation and execution. This means that we have to prepare the handover in the right time and execute to the handover the right time. Normally, the preparation and execution are very natural flow, and they are not separated. But in our case, we separated to procedure because they can help the increase the handover success rate. Okay, that's the technical characteristics of our mmWave 5G network. So I'm going to move to the demonstration of our use cases. As you can see, this picture, the right-hand side picture, shows the tethering by a vehicle scenario, which is described in the TR 3GPP technical report 22.886. In our scenario, overall, the concepts are the same. And in this scenario, we're going to provide gigabps data rate backhaul for this vehicle. And we want to provide very high-speed Wi-Fi services for the passengers inside the vehicle. This is the our test bed. This map shows the location of our highway test road and the Google map of the test road. In the test bed, we deployed about 5 DRU, also which is also a gNB, and each gNB site we have some equipment for fiber and power lines. And to the right-hand side, you can check the picture of our DRU equipment. And there is a control center, which has the server for L2 and L3 protocol stacks and 5G core networks. Also, in this test bed, you're going to provide a user experience for the passengers. They check some kind of services like video streaming, and also they check the Wi-Fi speed by the Apple named BenchB. Okay, here is some example of our measurement. Actually, in 2020, we provide a user experience for the 7 users, and they measured about several Wi-Fi speed, and we averaged the average speed is about 337 megabps. But in this case, we did not include the handover situation, because in that time our handover was not stabilized. So during the measurement, the user was inside the vehicle, and the vehicle was very slowly moving while they measured their Wi-Fi speed. And we also did the same demonstration in 2021. In that case, we did our best to stabilize the handover, so we could include the handover in the demonstration scenarios. And we got the average speed about 313 megabps, which is very similar to the value in 2020. But in this case, we included the handover. So I think the system was a little bit upgraded in that case. Okay, this was the brief demonstration of our use case 1. And I'd like to conclude. In our scenario, we developed mmWave 5G network for the application of Korean trial site use cases. In the use case 1, tethering by a vehicle scenario, we prepared a test bed at a highway test premise, and we also validated the mmWave 5G with a test vehicle. And we also provide the user experience for the high-speed Wi-Fi services, and they measure the Wi-Fi speed by BenchV application, and we also provide them the video streaming services. Also, okay, in the mmWave 5G network, we think that we could achieve a reasonable cell size by applying beamforming to the RF design and cell planning. And we also apply the beam switching to get stabilized performance while the car is moving along the car. And we also applied a combination of handover algorithm so that we can improve the handover success rate. And for future work, we think the mmWave system needs some more solutions for coverage holes. For example, we can use relay technologies like IAB, which means integrated access backhaul, XSM backhaul, or side link technology for V2X. So in the V2X, people are developing relaying technology, for example, UE to UE relay or UE to network relay based on the side link. And also there is a technology called RIS, which is hot issue these days, reconfigurable intelligent surface or reflective intelligent surface, which can be cost-effective solution for the relay. And I think we need also enhance the handover algorithm for the deployment in the city areas. Actually, we tested our system in the highway, but the highway is load is a little bit simpler than the cases of the situation in the city areas. So in that case, we need some more complicated and more advanced handover algorithm. Okay, that's it. This is the end of what I prepared for you. Thank you.
Thank you, Heesang. So, You-Jun, we move to you. I'll make you the presenter.
Okay, so just following the Dr. Chung's presentation, I will explain more about the remote control vehicle use cases. So remote control vehicle is used for the several usages. For example, the sudden weather changes, or the extend the conventional ODDs, or facing the unusual situations during the automated vehicle operations. So this source is defined the ISO TC204 working group 14, and this kind of the working item is now developed to the technical effort as the information standardizations. So there are several technical efforts regarding the remote control vehicles that we are referring to the 3GPP technical effort 22.886. And in this document, the functional requirement and KPI is defined, as you can see in the red box, in terms of the uplink video streaming data rate and reliabilities. And also the 5G AEA They published the technical report regarding the CVTech use cases and service level requirements. And in the document, there are three teleoperated driving use cases. One is the teleoperated driving and teleoperated driving support and teleoperated driving for automated parking. So this is the general description about the teleoperated driving that is defined in the 5GAA document. As you can see in these tables, the teleoperated driving is to provide to the vehicles that is remotely driven the appropriate trajectory and maneuver instructions to navigate to the destination efficiently and safely. And it also defined the service level requirements in terms of the ranges and informations requested and generated, and latencies, and varieties, and extras. So in our use cases, we define the KPIs, the downlink data rate and uplink data rate, and HD video streaming up to 15 Mbps, and 4 live video streams, which is the front, rear, left, and right side to deliver to the remote drivers, and latencies and around the view monitoring video stream to the servers, which is only activate when the parking mode or the reverse driving mode. So this slide shows the system architecture of the remote control vehicles that we have developed. So as you can see in this slide, the remote driving system is designed to comprise the two key components. The first one is the remote control driving systems in remote control vehicle and remote control stations. The remote control driving system in the vehicle is responsible for providing a remote operator not only with the vehicle control functions, for example, brake, acceleration, steerings, and turning signals, but also with the status monitoring functions, for example, vehicle speed, steering wheel angles, and turning signal status, extras. As you can see in the left side of this slide, using high definition cameras on the remote control vehicle, the around view monitoring and real-time visual sharing units stream the around view and front, right, left, and rear situation videos of the vehicle to the remote control stations, respectively. The vehicle gateway of the remote control driving system is designed to receive the vehicle status messages such as the steering wheel angle, vehicle speed, and RPM, gear positions, and extra from the in-vehicle networks. The in-vehicle network is composed of these 6 electric control units, each responsible for different signals. For example, there is the body control modules and engine control modules, automatic parking brake, and intelligent dynamic modules, and electric power steerings, and transition control modules. So to access these ECUs, we can control the remote control vehicle by the CAN messages, and there is the CAN to Ethernet conversion modules that receive the vehicle status messages from the vehicle gateway with the CAN protocols and transmits them to the remote control stations with the TCP/IP protocols every 10 to 15 milliseconds. Remote control station that is depicted in the left side of this slide is provide the remote operator with the various information, including vehicle status, around the view for the parking safety and convenience improvement, and real-time view of the current road situations. The operator can check the vehicle status on the cluster and dashboard in the remote control stations, and the around the view and the real-time the road situation view are displayed on the dashboard and 4 screens displays respectively. Remote control station also generate the control inputs and in terms of the VTX signals and send them to the remote control driving systems every 10 milliseconds via the mmWave 5G NR communication link that is provided by the ETRI. Specifically, signals for brake, acceleration pedal positions, turning in angle, and hazard ramp are sent to the ECM and IDM and BCM respectively, and the other control signals, for example, the turning signals or gear positions, are directly sent to the ECUs of the remote control systems. Then the ECUs delivers the collective control signals to the CAN to Ethernet modules with the CAN protocol, and the CAN to Ethernet module sends them to the remote control driving systems with the TCP/IP protocol every 10 seconds via the mmWave communication. So I'm going to explain more about the remote control vehicle systems. So remote control driving system consists of the around the view monitor units and real-time video streaming units and vehicle gateway units, as you can see in this slides. In the AVM and real-time video streaming unit, there are 5 VTX modules stream 5 HD videos to the remote control stations via the mmWave band vehicle communications using the TCP/IP protocols. In the real-time video streaming units, there are 4 VTX modules receive the rear, left, front, and right side of the remote control vehicles via the LVDS interface, and then AVM unit makes the high definite around the view image using the another 4 HD cameras on the front, left, right, and rear side of the vehicles, as you can see the right side of this slide. So this slide shows the remote control stations. So we are using the automotive part for the generate the more precise the control inputs. So we tear down the our test vehicles and then reconstruct it as the remote control stations, as you can see in the right side of figures. So the real-time remote control station consists of the control input generation unit and road situation monitoring unit and vehicle status monitoring unit, as you can see the left side of these figures. The control input generation unit the body control modules and engine control module generate the turning signal and steering wheel angles and acceleration and brake signals, and broadcast them to the remote station control board with the CAN-D protocols. Remote station control board also requires the parking brake and gear positions and hazard ramp signal from the parking brake switches, E-shifter and hazard switches respectively with the analog input, and sends it to the CAN to Ethernet module with the CAN protocols. Then the CAN to Ethernet module converts it to the TCP/IP protocol and transmits it to the remote control driving systems via the mmWave communication. The road situation monitoring unit receives the 4 video streams from the remote control driving systems and displays the videos for the front, left, and right and rear views on the display monitors. And vehicle status monitoring unit receives the vehicle status data from the remote control driving systems and then display them on the cluster and the dashboard that is mounted on the remote control stations. So this slide shows the system configuration about the around the view monitoring systems. The AVM is a system that provides the HD 300-degree around the view images of the situation outside the vehicle in real time. The AVM image is composited with the real-time distortion correction using the 4 HD images taken by the cameras mounted in the front, rear of the vehicles and under the left and right side mirrors. So it provides the drivers with the around view images as if seen from the sky for the high-stop parking safety and convenience. And AVM automatically started when the gear selection is put into the reverse mode while the vehicle is started, and changing the gear from the reverse to park mode, and it starts the AVM operations. So this slide shows the real-time video streaming system. So in the real-time video streaming systems, there are 4 VTEX modules streaming the 4 HD videos to the remote control system based on the RTP protocols. And in the system, the LVDS serializer transforms the 10-bit wide parallel HD low voltage data into the serial high-speed LVDS data streams, and VTEX modules then encoded into the H.264 videos and make it to the moving picture export group transport streams, which is the MPEG TS format, and transmit it to the remote control servers using the TCP IP protocols. So as you can see in the right side of the pictures, this is the video streams that generated by the real-time video streaming that is mounted in the remote control vehicle and then transmitted to the remote control servers. So this is the system integration with the mmWave, which is the 23 gigahertz. So I'm not going to explain more detailed about the mmWave systems because Dr. Chung is explained about it just previous presentation in detail. So we integrate it. We integrated the remote control driving systems and remote control systems with the millimeter wave communication link, as you can see in these figures, and then send them back the vehicle status data and control inputs, both from the remote control vehicle and remote control stations at the same time with in very high speed. So this slide shows the field test environment that is at the KATECH, the proving ground. So we're providing the approximately the 470 meters test track, considering the maximum transmit the range of the millimeter wave communication link. So we set all the millimeter wave system in the the test vehicles, as you can see in the right side of the figures. So there are the gNB data unit and the gateway and 5G core networks and gNB CUs. And in the test vehicle, there is a vehicle UI. The L1 and RF is mounted on the top of the vehicles. And then router and vehicle UI L1, L2 is set up on the trunk of the vehicles. And there are 8 cameras, the front, left and right and rear side to generate the real-time video streaming, and AVM is mounted on the around the vehicles, as you can see in these slides. And you can also see the test parameters of the millimeter wave communications just right side of these tables. So this slide shows the example of on video clip for when the displaying the vehicle status data in the dashboard that is received from the remote control vehicle through the millimeter wave communications. So as you can see here, the gear position is changed depending on the gear positioning status inputs, and then the RPM is also changed according to the RPM status input that is received from the remote control vehicles. And this slide shows the test results. So the left side is the remote control vehicles and right side is the remote control stations. So the control input generated by the remote control stations and then transmit to the remote control vehicles via the millimeter wave. And accordingly, the vehicle status data and the video stream images is generated by the remote control vehicles and then transmitted to the remote control server through the millimeter wave communication link. And as you can see here, the average data rate is the approximately the 50 Mbps. So this is my last slide for the my remote control use cases. That is lessons learned on the 5G for the camp. So we experienced that the uplink is more important than the downlink in the remote control vehicle use cases to providing the real-time video streaming to the remote control servers, because the control input is data rate of the control input just a few megabytes, while the video streaming data or the sensing data is the more than 40 or 50 megabyte. And multi-beam switching, that is the one of the core technology of the millimeter wave communication, is the very important technology to cover the real driving situation. For example, when you're considering the narrow beam width, which is the 18 degree, if you remember the Dr. Chung's presentations. In case of the lane changes or the turn left or right examples. And the last lesson that we learned from our field trial is the generation of the precise control input. Is the important to control the remote control vehicles more precisely, because if you generate the control input used based on the some kind of joystick, for example, then it is kind of hard to generate the very precise control inputs, and it affects the precise control of the remote control vehicles. That is why we use the we make the control station based on the real automated the parts after tearing down all the components, and then so this is the all that I prepared today. And if you have any questions, then please.
Thank you, Heesang. Thank you so much both for your presentations. I know there was also a video. Do you think it's a good time to show it now?
Yeah, so we have the one video that is from the ETRI regarding the tethering use cases. So if you can share, then please share it to the audience.
All right, perfect. Give me 1 second. So this is the use case on tethering.
Exactly.
All right.
Okay, so this is the demo video that we took from the when we reviewing from the Korean the funding agencies.
Great. Thank you, Heesang, also for sharing this video. It was really interesting. And now we are opening the floor for a discussion. We have 15 minutes, so please feel free to type your questions to the question box. You can also indicate the speaker you're directing the question to. And I can see there is already one question. Give me 1 second. I lost my panel. All right. For millimeter wave, as mentioned, coverage is more difficult than with lower bandwidths. What is your view on the sensitivity of remote driving when using millimeter wave? That is the first question.
Okay, so we experienced a lot of the sensitivity issues when we testing the millimeter wave based on the millimeter wave communication link. So we are facing some kind of the issues when we just fix the power of the millimeter wave link. Then in some point there is the signal losses for uncertain regions, and so that is why we apply the ETRI. That we applying the power control system depending on the signal levels, if I understand correctly. So there are a lot of things that we have to improve for applying the millimeter wave system on the real environment, especially the urban areas. So if the and also the actually they are also more experienced about the testing millimeter wave in real load situation. Of course, it is even in the highway situation. So if you're adding more comment from the millimeter wave, the usage utilization, then please adding your comment on the Dr. Chung.
Okay, I think the question is about the remote driving cases, but talking about coverage issues, yes, it really has. A millimeter wave has issues about the coverage. Actually, in our test road, in highway test road, there were some blockages like a bridge over our test road, and we usually experience the connection loss at the when we approaching the bridge, but we usually drive the car with about the speed of 500 kilometers per hour, so the time was very short in this case. But if there is some traffic jam, we have to deal with that kind of subbridge data disconnections. So I think millimeter wave is more sensitive, more delicate, and more sensitive compared to the lower frequencies. Surely it has the coverage issues and coverage hole issues compared to the other frequencies. And that's my comment.
And if I may add or more comment, then I briefly mentioned about the standardization activities in the ISO TC204. The remote control vehicle is used in some unusual or the specific situations. For example, the sudden weather changes or the out of the ODD situations. So in that case, the millimeter wave is very useful to overcome the very hazard situations, because the remote control vehicle use case requires the high data rate to transmit the sensing data, but also the high definite video data to the remote control servers in real time. So I think that the remote control vehicle use cases is more suitable for the unusual use cases, not for the just normal driving situations. So this is my comment from my experience about the use cases.
Great. Thank you both. Have another question. I'm not sure if it's related. Your millimeter wave 5G system is using around 22 gigahertz radio frequency. Is there any specific reason for choosing that frequency?
Okay, thank you for the question. Actually, in our country, Korea, we have 3 mobile operators, and they have 2 band. Each they have 2 band. For example, they have for sub 6 gigahertz, they have 3.5 gigahertz band, and they also have above 6 gigahertz spectrums. For example, the 28 gigahertz band. So if we consider this situation, we may choose 28 gigahertz band as a baseline frequency, and that is one option. And another option, there's another option, which is around 22 gigahertz that we developed in this system. Actually, this frequency band was announced as a FACS spectrum, which means flexible access common spectrum, by Korea government. So they intended to encourage the industry to use millimeter wave. And if we use that frequency, we can use that frequency without a license. So if we have millimeter wave 5G solutions based on this frequency, the third party, for example, another service provider, which is not mobile operators, can learn a business based on this frequency. So I think developing this 5G millimeter waves system based on this frequency may help to this kind of business model. And that was another option. So we thought about that, and that is one reason we chose that frequency as our spectrum. Is it okay?
Of course. Thank you. Thank you for your answer.
Thank you.
You-Jun, do you want to add something on this, or shall I move on?
But actually, I'm not the expertise about
Right.
the precaution things. So
No problem. I thought so. All right, then perhaps another question for you. Can you tell us more about the status on available services based on millimeter wave 5G in Korea? Perhaps you or Heesang.
Okay, maybe I can.
Okay, it's for you again. First, go ahead.
Okay. Actually, we have many trial services for millimeter wave 5G systems, but until now, we do not have any commercially available services using the millimeter wave band smartphones. So in Korea, you cannot buy a millimeter wave supported smartphones because there is no commercially available service. But the mobile operators, we have 3 operators, KT, SKT, and LGU+. They have been doing many trial services. For example, recently, KT, in a baseball park, they have been running 28 gigahertz 5G system for virtual reality, VR services, or gaming services, and 8K video streaming services. And another example is SKT. SKT is running 28 gigahertz 5G system for a robot for information in a building. But these are not commercial services. They are just trial services. So I hope that someday we can see commercial services. But meanwhile, there is some notable activities in the 28 gigahertz system these days. The 3 mobile operators together has been deploying 28 gigahertz 5G infrastructures in Seoul metro systems. So I think the passengers will be able to use Wi-Fi services based on their system. The concept is very similar to the tethering by a vehicle. So in our system, we used a test vehicle, which is a small bus. But in this case, the use cases for the Seoul subway system. So if they finish their deployment, I think the Seoul citizens will experience the very high speed Wi-Fi speed based on the 28 gigahertz infrastructures. So I expect this kind of services will soon emerge. And yes, this is what I can say about the 5G services in Korea.
Right. Let's see. The future is close.
Yes.
Another question coming in from the audience, from Vasiliki. What are the quality of service management functions used by the 5G system? There was no PCF function in the 5G core, I think.
Yes, that's good questions. Actually, the 5G core network was developed by SNET ICT, which is one of our partners in our 5G MOBIX Korean trial site. And in this system, they just developed core functions for the 5G core emulations. So they did not include the PCF or other function blocks for this system. So I cannot comment more about the situation, but in our systems we only included 3 functions: SMF, AMF, and UPF. So the PCF, I think, is a policy function. I think we did not include that kind of functions in our system. That's a pity.
All right. Thank you, Heesang, for. So Vasiliki also thanks you for the answer. Yes.
Thank you.
As now we approach to the end of our planned agenda, I would like to also ask you, You-Jun, is there anything else you would like to touch upon before we conclude? Any wishes for the future? Any advice?
Okay, so because in Korea side we are developing our own 5G networks, which is the millimeter wave. So and it is not provided by the mobile network, the providers, for example, Nokia. So the functions of our system is very limited, but we are testing our systems based on our own systems. So we think that there are the bunch of things we have to develop more about it to deploying this kind of systems in the real world. As the Dr. Chung from ETRI mentions for the various subsystem models. So as the automotive fields, we are also thinking that how can we bring this kind of the 5G technologies into the automotive fields. So we are thinking that the just close the area services, for example, the automated parking systems. So this is this will be the next future project based on the mmWave or the communication link with the automated vehicle technologies. So that's all the comment. And
Great. Looking forward to what's coming next.
Yep.
Well, we are now almost arriving to the end of the program. So I want to thank you both. Thank you so much, Heesang and You-Jun, for your great presentations and your inputs. And thanks to the audience for being part of this event. I also want to go to my last slide. I hope you can all see it. And just before we sign off, I would like to let you know that there is an upcoming webinar, and it's actually the last webinar of this webinar series from 5G MOBIX. It's next week, next Friday, sorry for the typo, and it will focus on the Chinese trial site. So we hope to see you there. And in case you want to catch this or any of the previous webinars, you can always go to the 5G MOBIX website, and under the resources you can find the page dedicated to all the webinars of the project. And with this, I want to thank you all for joining us. Thank you, Heesang and You-Jun, again. And
Thank you for your attention.
And have a great rest of your day. Thank you.
Thank you.
Bye.